This is my lab 4, which is oscillations. Introductions. The focus of this lab was to model oscillations computationally and identify elements of oscillation and calculate their components. The purpose was to implicate things such as Hooke's law, potential energy, and periods of oscillation to create a model of oscillation. Main ideas: we have the period of oscillation, which is given by 2 pi square root mass over k. We have Hooke's law, which is mg equals ks L minus L naught. Potential spring energy, which is 1/2 k s squared, which that k is not to be mistaken with the previous k stated. That the k in that is the kinetic energy and not the spring stiffness. And then the potential energy of gravity is mgh. Brief overview: this lab determined that the L naught value for the spring is 0.013 meters, with the spring stiffness being k equals 5.745 newtons per meter. Procedure: the first step was to analyze a given video of an oscillation of a spring using Tracker. The second step was to export that data to an Excel sheet. The third was to modify code to match the data in Tracker. And the fourth step was to compare. Tracker. This is the screenshot from my Tracker. We can clearly see the oscillations. And the system was the spring and the ball, and the surroundings were everything else, with the initial conditions being zero velocity, which means no oscillations. Here is some of the math that I used to calculate what L naught should be. So I set the force of gravity to the force of the spring, and ultimately we get this value of L naught being L minus mgr, and when you substitute in all the values, you get 0.0153, with the mass being 0.402 kilograms, and gravity, of course, being a constant 9.8 meters per second squared. Code. Here is a screenshot of my code, and here are some of the edited lines. We have the mass, the vector position, the timing, and then of course all of our data. So this was the L naught value that I calculated. And then here is a highlight on some of those values. And then we defined initial energies right here. The gravitational force, which of course being the negative mass of the ball times gravity. And then we have F spring right here with F net. And then of course we have the momentum principle right here, and then updating the spring. This was my final graph, which didn't make too much sense because as the code was going, it would oscillate, but for some odd reason it would only present the oscillations here at the end. So when the code was running at time 0.5, there were oscillations, but in the final graph it just didn't show. I'm not too sure. Similarities: the oscillations at the end of the graph were similar to those given in Tracker, but of course the difference being that the Tracker graph obviously had more oscillations. What does it mean for your model system? Is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. My model system was definitely incorrect, and realized that if there were more oscillations similar to those at the end of the graph, then it would be correct. The green line and the orange line would need to be off the zero for the x-axis in order for the values to be correct. And then the second what does it mean question: using the data you obtained in Tracker, make 2 separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position. Compare the 2 estimates and discuss. The x position, as I discussed before, I believe would be about 1.662 seconds, and then the y position would remain the same due to the oscillations and their axis differences. And my conclusion is that this lab demonstrates how to analyze, computate, and create models for oscillation.